Okay, so now we'll look at some of the commands involving hypothesis testing. Uh, as before, I'm going to just show you the scripts, and then we will see how does one perform the test using the scripts. Uh, we are not going to delve too much into under what circumstances does one apply a z-test or a t-test. So in this video, we're only going to focus on if you have to apply a z-test, how does one go about it, or if you have to apply a some other t-test or an chi-square test, how does one go about it. So let's start with a simple one. So we are going to start with a scenario where n is greater than 30, the population variance is known, where we normally apply z-test. And so say the mu is 7.5 and the population standard deviation is 0.66. So these two are, so the population standard deviation is null. And the null hypothesis in this case is that x bar, which is nothing but the mean of log MPC, is greater than mu, and n equals to 100. So one simple way of calculating is, let's compute the test statistic. As we know that the z test statistics is x bar, which is mean log of MPC minus mu, divided by the standard error. The standard error is nothing but the standard deviation divided by the number of by n, where n is equals to 100. So let's kind of apply that, and what we get here is a value of 4.173413, and let's look at the cumulative probability of 4.173. So let's kind of copy this, okay, and let's put the cumulative value of 4.173, and if we run this, so we get a value of 0.9999. So, and what does our p norm suggest? P norm was, let's go back to the p norm, and the p norm was when that the lower tail was true. Okay, so this was our p norm. So this is basically what is the probability that given a mean of 7.775 and standard deviation 0.64, what is the probability that x is takes any value less than equal to 9. So this is nothing but the probability p norm 4.173 is nothing but what is this is the probability up to that point. And therefore the inference from this, where our log of MPC mean was 7.775, so this is basically we are going to accept the null hypothesis that that indeed this is greater than equals to the mu, which is 7.5. So how about using t-test? So here we are going to look at some one sample mean. As we know that one sample mean using t-test are done when either n is less than 30 or whether the standard deviation is of the population is not known. And the simple command in R for a one sample two-tail test is a t-test log of MPC mu equals to 8. So this is basically the null hypothesis in this case is that we are testing for that x bar, that is log of MPC is equals to 8, and against an alternate hypothesis that it is not equals to 8. So let's run this one, and what we get, the value is minus 10.1783, and with a p-value of extremely small, close to 0, and therefore the null hypothesis that they are equal because it's a two-tail test, so that gets rejected. What about one sample upper tail? So here we have to specify the alternative is equal to beta, that's for the upper tail, and if we run this, what we get is that again the value of p is extremely small, and therefore the probability that that x bar is greater than equals to 7, this time that hypothesis kind of gets accepted, because had the calculated value, if the calculated value was such that it was less than, let's say, 7.773, then we would have had a sorry, if the interval was within 7.773 and infinity, so we would have said it's greater, and what we get is 35.14, which is a p-value of very close to 0, and therefore we are going to infer that even in this case the hypothesis that the log of MPC is greater than 7, that gets accepted. Let's look at the t-test for two sample and two-sided. So as we know that this is for it doesn't have to be an equal number of observations on either side. So what we are going to test here is we are going to look at the household size, and we are dividing the population according to poverty into two groups. People who are above, households who are above the poverty line, and households who are below the poverty line. So as you recall, that poverty was a variable with ones and zeros. So all households with a value of poverty equals to 1 are below the poverty line, and all households with poverty value equals to 0 were above the poverty line. And basically this test is looking at is there any significant difference between the average household size between the two population groups. First population group being one above the poverty line and the second being below the poverty line. So mu equals to 0, which means we are testing that the household sizes are equals to 0. This is a two-sided because we are testing whether they are equal. We specify confidence level of 0.95. We say that the variance is not equal. We have no reason to impose the variance being equal, and it's not a paired. So paired equals to false because we are not doing a matched pair test here. So if we do this, okay, so what we get, again the value of t is minus 11.3887, so which effectively means and the p value is extremely small. This number doesn't fall in this group. This is the mean in group 0. So these are the mean household size for people who are below the poverty line. This is the mean household size for people above the poverty line, and this is the confidence interval level. And since this is outside the interval level, shown by the fact that p-value is very small, so our null hypothesis that the average household size between the two groups are equal, that gets rejected. What if we were to do a one-sided, and for that let's we run it. So here the hypothesis is that we are looking at only one side, and where we are looking at whether the household size is less than the household size for people who are below the poverty line is less than household size of people above the poverty line. And there again we get the test statistics is the same, that doesn't change, only our inference will change. We again find the value of p equals to 2.20016. So therefore this time our null hypothesis that the household size of people below the poverty line is less than the people household size of people above the poverty line. So if our null hypothesis is that household size of people above the poverty line, and compared to the household size of people below the poverty line, if we are making these two comparisons, then we have to reject the null hypothesis that the household size of individuals, household size of people below the poverty line is greater than household size of people above the poverty line. Okay, so that's how we run the test. So as again from the original statement, we have to create the null hypothesis and the alternate hypothesis, and thereafter we look at how to run the test. So in the classroom we will discuss more about, in a given scenario, how to form the null hypothesis and how to infer. But in this video we are only looking at how does one run the scripts and get the necessary calculations. Finally, let's do a test of two sample variance. So for that, let me draw a random number, 50 random numbers with mean 0 and standard deviation 2. So let me call it x1. Let me draw another set of random numbers x2 which are the 100 random numbers with mean 1 and standard deviation 2. And let me just pick up a sample of n equals to 40 from them. Okay. Okay. So sorry, we don't need this. So now let's do the two sample variance. So here we are looking at whether the sigma 1 square and the sigma 2 square, whether the variance between the two are the same. By construction, we have made them to be the same. So we put the ratio is equals to 1. So if we were to test that whether the variance of this is greater than this, then we would have a ratio greater than 1. So the alternative is a two-sided test, and we have a two-sided test because we just want to infer that these two are not the same. Yeah, we are looking at whether these two are the same or not, and let's see how does one run those tests. So we do a VAT test. This is the variance test, and we get a p-value which is an extreme, is pretty high. So therefore, we cannot reject the null hypothesis that the two variances are the same. Had this number been extreme, been less than, let's say, 0.05, would have been at a 95% confidence level. Would have said that these two variances are not the same. But in this case, we are going to say these two variances are same, and that's not surprising because that's the way we have done it. On the other hand, if I now do an x3. Say I do an x3 where again I draw 100 random numbers. I don't tamper with the mean, but I make the standard deviation 4. And if I were to now run the variance test between x1 and x3, and then suddenly we find that the p-value is extremely small, which means now the null hypothesis that the variance of x1 and x3 being the same, that now gets rejected. So clearly these two, when we are doing x1 and x2 variance, our inference was that they are not getting rejected. So which means the null hypothesis that x1 and x2 is the same variance, that gets accepted. However, when we look at between x1 and x3, then our null hypothesis that the variance of x1 and x3 is the same, now that gets rejected. Okay, let's quickly do a one-way ANOVA table. So basically, there are many cases where we do ANOVA, and it's probably always a good idea to do a little bit of ANOVA before we get into regression. And to do that, let's do a simple box plot. And we want to do a box plot of log MPC and social group. Okay, now before we do that, let me clear the plot area. I can also clear the by doing in Control L. I can clear the console, and let's do a box plot. And this is what we get. So therefore, what the box plot gives us an idea is that among the 4 social groups, and if you look at the average log of MPC values, it appears that the OBC, SC, and ST, their average average of the log MPC is very close to each other, whereas the other group had a significant higher log of MPC. So it appears, from the figure itself that probably when we look at a log MPC, and then the log MPC does differ across the groups. So let's do a simple ANOVA, and then if we do a summary of the ANOVA table by the AOV command, we find indeed that the null hypothesis that all the log MPCs are the same, and they get rejected. And therefore the inference is that not all the log MPC values are the same across the 4 groups. Now, and that is inferred from the fact that the p-value is extremely small. However, what it doesn't tell us is that the null hypothesis which gets rejected, which means where H naught is where the H naught was this is equal to this, equals to this, equals to this. So when we reject this, we do not know whether none of them are equal or some of them are equal or few of them are equal. So we don't know that. So to know where the inequality creeps in, we must do the Tukey test, and let's run the Tukey test. And then let's plot the Tukey. It gives a nice simple table, and this should tell us, where are the differences. So the way to read it is between others and OBC, the p-value is extremely small, which means there is a difference between others and OBC. So others minus OBC, the difference is 0.40, so the log MPC is greater than the log OBC. Between SC and OBC, this value is 0.41, so this is not significant, therefore there is no difference between SC and OBC. There is no difference between ST and OBC in terms of log of MPC, because even this is reasonably high, whereas there is a difference between SC and ST, where the others log MPC of others is more than ST as well as from than ST, and there is no difference between ST and SC. So a simple way of interpreting is that there is no difference between SC, ST and OBC. The difference between SC and OBC is not high. The difference between ST and OBC is not high. The difference between ST and SC is not high. However, there is a significant difference between others and OBC. So this is significant, and so are these two. And if I just do a simple plot of TK, we get exactly that's the inference that this is the zero difference, and we find that the difference is significant in terms of how the values change. Okay, so let's kind of get into some regression. And for regression, we will first learn to define what we call a global variable. And to define a global variable, the advantage is that I will not have to every time write the variables instead, but I group the variable. So I group the variables using the command cbind. So I group the variables called assets, where I collect all the assets, and I group the variables in asset using the cbind command. I also use demography to use all the variables which are demographical in nature, the religion and the social group, as well as the household size. And finally, I group another variable called access, which is LPG and electricity. And the idea behind defining a variable access is these usually are the this is what the government gives access to. So where assets are what individuals, households have. Demography is usually what households are born with, and this is what is the government access programs. So let's run it, and now these are ready, and we will do a simple linear regression. So, but before we do that, let's do a single variable with log MPC and household size. And we see that, as before, that there appears to be a negative relationship between log MPC and household size. Let's do a simple regression where we define the regression equation as OLSRG. LM is for the linear model, where log MPC is my y variable, this is my x variable, and the data which we are using is DE2. If we do not use data equals to DE2 because we have already attached that, it shouldn't be a problem either. And then if we just run this regression, the regression has been run, and to see the summary output, that's how the summary output looks. It's a simple regression. So we have an R-square value of about 17%. So 17% of all fluctuations in log MPC are explained alone by the household size, and the household size is significant with a negative coefficient. So effectively it means that for other things being constant, if we compare two households, if the household if household B has one member more than household A, then the log MPC of household B will be lower by minus 0.12 than compared to household A. Next is the best fit line. So this is the best fit line we have, and so indeed, this is the best fit line where the intercept is 8.21 and the slope is minus 0.12. We can also do multiple regression, and in multiple regression now we want to include all the variables. The y is log MPC. In the x variables we include the assets, the demography, and access. So if we do this, and if we look at the summary OLS regression, what we now get is is the significant variables are, having a radio is a significant variable. So households having a radio is more likely to have a higher MPCE. Households having ACs are more likely to have higher MPC. However, households having stoves are likely to have lower MPC, and that is partly because households which use stoves as a primary cooking medium are most likely they don't have LPGs, and they rely on kerosene, and kerosene typically is a targeted subsidy for the below the poverty line. Households having fridge has a higher MPC than households which do not have fridge. This is no surprising that the households having cars are more likely to have higher MPC, and in fact even the signs look all right, and so does the magnitudes. Having a car is more likely to be not poor than having an AC, than having a fridge, than having a fridge, than having a fan. And whereas households having a stove are more likely to be poor. When we go to the demography, we find that the household class of SCs and the OBCs, they are more likely to be poorer than people who are not, and indeed households with a higher size, they are also likely to be poor. This has an overall adjusted R square of about 60%, so it's a reasonably good fit, and therefore one can refine this model and do a predictive modeling of the same. And so we can plot the OLS, and then if we hit return, so these are the scatters, and this is the plots which we get, and we will interpret the what are the ones which are outliers and which we are not, and those we'll be doing during the course. Some final word before we end this video. To save the work, what I normally do is I go to file, I save it as something called try or try1. So this is the initial command, so this is going to be try. So the next time I can straight away open the try command. For other commands, how to do the statistical distribution and other statistical tests using R, you can visit rtutor.com, and that's how the RTutor, this is what the homepage of RTutorial looks like. You can also use this book, which is by Mark Gardner. It's called Beginning R, a statistical programming language. It's a Wiley India Private Limited. It's available from Amazon, and it's not very expensive. It's about 649 rupees. There are some useful websites as well, and you can check some of the YouTube videos. The basics of R, Ed Boon and Phil Chan has a whole set of videos which explain how to do the basic operations in R with various examples. And I also suggest that you can have a look at the YouTube video by Econometrics Academy, because they have separate videos on the underlying concepts, and then they have videos on how to perform them in R. Okay, thank you. So I hope this video was useful to get started in R, and then in the classroom we will actually look at the background concepts and run the scripts, and we will try and interpret the results in more details. Thank you for listening to the video.